In this video, I'm going to quickly go over 10.2 as a review. This is calculus with parametric curves. So first we're going to talk about the tangents of the parametric curves. Suppose f and g are differentiable functions, and we want to find the tangent line at a point on the parametric curve x equals f of t, y equals g of t, where y is also a differentiable function of x. Alright, so then we'll have the chain rule that gives dy dt. Alright, and then if dx dt is not 0, we can solve for dy dx. So here's our equation for dy dx. So dy dx equals dy dt over dx dt, assuming dx dt is not 0. So equation 1, which you can remember by thinking of canceling the dt's, enables us to find the slope dy dx of the tangent to a parametric curve without having to eliminate the parameter. Right? So that's the slope, change in y over change in x. We see from 1 that the curve has a horizontal tangent when dy dt equals 0, provided that dx dt is not 0, and it has a vertical tangent when dx dt equals 0, provided that dy dt is not 0. This information is useful for sketching parametric curves. It is also useful to consider the second derivatives. So this can be found by replacing y by dy dx. All right. So you'll see here d dt of dy dx over dx dt. A curve C is defined by the parametric equations x equals t squared, y equals t to the third, minus 3t. So we want to show that C has two tangents at the point 3, 0, and then we'll find their equations. Find the points on C where the tangent is horizontal or vertical, and determine where the curve is concave, upward or downward. All right, and then we'll sketch the curve. So we'll go through each one of these. Okay, so this one we want to find the two tangent lines or equations. So we'll notice that y equals 0 when t equals 0, or t is plus or minus square root of 3. Again, we've got a cubic, right? So we're going to have three answers for this. Therefore, the point 3, 0 on C arises from only two of these values, right? Because when you plug in 0, your x is t squared. So when you plug in 0, you get 0, 0. But if you plug in square root of 3, you get 3, or negative square root of 3, you get 3 as well. So the only values are plus or minus square root of 3. So this indicates that x crosses itself at 3, 0. Right. So we know that the slope, right, we want to find the slope, the derivative of x dy dx is just dy dt over dx dt. All right. So we go ahead and simplify that and plug in t equals plus or minus square root of 3. We get plus or minus square root of 3 for the slope. So we have the slope intercept form. Oh, sorry, slope point form, right? So we got the slope and our point 3, 0. Or 0, 3, sorry, 0, 3. And our slope negative square root of 3, and our point 3, 0 again. So the point slope form here, and we've got our two tangent lines. All right, so for B, C has a horizontal tangent when dy dx equals 0. That is, when dy dx equals 0 and dx dt is not equal to 0. So we're finding the horizontal tangent. Since dy dt equals 3t squared minus 3, this happens when t squared equals 1. So that is t would be equal to plus or minus 1. So the corresponding points are 1, negative 2, and 1, 2. C has a vertical tangent when dx dt equals 2t, which equals 0. That is, when t equals 0. All right. So the corresponding point on C is 0, 0. All right. So to determine concavity, we have to calculate the second derivative, right? So we take dy dx dx dt, and we take the derivative of that. And we'll end up with this. All right, so we see that the curve is concave upward when t is greater than 0, and concave downward when t is less than 0. All right, so here's our curve, and we're able to kind of sketch it knowing that information. You can see these crosses, these two tangent lines. All right, so area. So we know that area, right? Area is just the integral of f dx from a to b, right? Assuming f of x is greater than or equal to 0. All right, but using substitution rule for definite integrals, we can take our parametric curves, f of t, g of t, from alpha to beta, and substitute that in. All right, or we can kind of write it like this as well. So the integral from alpha to beta gt f prime gt dt. All right, so that's just substituting. So we're finding the area. Here's an example. Finding the area under one arc of the cycloid. All right, cycloid. X equals r times theta minus sine theta. Y equals r times 1 minus cosine theta. All right, so here we go. We're just finding the area here. 0 to 2 pi. All right, 0 to 2 pi. Using the substitution rule, right, we've got our y equaling r times 1 minus cosine theta, and dx is going to be, right, this is gt prime d theta, or sorry, gt theta, g theta prime times d theta, right? So we go ahead and we substitute, right? So I'll show you here. This is y, and here you go, is g prime theta d theta. And we go ahead and do the integral. And you get 3 pi r squared. All right, now to arc length. From chapter 8, I believe, you learned that arc length is the integral from a to b, square root of 1 plus dy dx squared dx. All right, so this is going to give you a length. So suppose that C can also be described by the parametric equations now. So now we're going to move on to the parametric equations, f of t, g of t, from alpha to beta. Okay, so where dx dt, which is f prime t, is greater than 0. All right, so you can look through the book in 10.2 to read through this, and we end up with, right, so we end up with theorem 3 here, which then takes us to talking about even if you can't express it as a function of x, we still get our length okay, so this is the length of your parametric curve. Is going to be your integral alpha to beta square root of dx dt squared plus dy dt squared dt. All right, so you should know this equation, right? Okay, so let's do example 4 in the book to kind of show you how to use that length, the arc length equation here, or arc length formula. So we know we can represent the unit circle as cosine t. I'm going to try to quickly do this because I'm running long here on this video. So we know that dx dt is equaling negative sine t. dy dt in this situation is sine, cosine t, right? So we can go ahead and use the arc length equation. Zero to 2 pi square root of dx dt squared plus dy dt squared, and that's dt. All right. So real quick, we plug in our values. Oops, put a parenthesis there. Sine squared t plus cosine squared t dt. And that's just 1, right? So we've got 0 to 2 pi dt, which will be 2 pi, right? So you found your area of your unit circle to be 2 pi, right? 2 pi r equals 1. If we were to do this again with cosine of 2t, your x being equal to cosine 2t and your y equaling sine 2t, you'll notice that the integral will give you twice the arc length of the circle, right? So it's going to give you the length here of this one's going to give you actually 4 pi. It's going to take you around twice.